Good afternoon, everybody. My name is Charlie Nicklin. I'm the Chief Executive of IAgrE, and I'd like to thank you all for joining our February presentation. I'd like to welcome IAgrE member Dr. Rob Simmons for our lecture today. Rob is a reader in sustainable soil management at Cranfield University and has over 30 years laboratory and field-based experience in both the UK and overseas. Rob's current focus is soil erosion on horticultural crops, along with soil management solutions to promote seed emergence and establishment. In today's lecture, Rob will present to us how polymers are being used in this particular area. As usual with our lectures, everyone will be muted. If you would like to ask a question, please pop it in the chat function at the bottom of your screen, and at the end of the presentation, we can unmute you so you can ask in person. Okay, I'll now hand over to Rob.
Right, well, thank you very much for this opportunity. I would like to talk today about, as it says here, about polymers and the role of polymers to enhance emergence and stand establishment, promote improvements in yield in high-value horticultural crops. This is research that we've done in collaboration funded by SNF, largest global producer of polymers, and in collaboration with G's and Watts Farms. And what I'll do today is I'll give you a little bit of a background on what we've been doing and some of the challenges around that, and then go into detail on the salad onion trials that we did last year, as well as the spinach and the parsley trials. So some of the key challenges for these high-value horticultural crops is that there are intense tillage operations associated with them. They tend to be grown on the lighter textured soils, which have essentially over the years been degraded in terms of their structure. They're very prone to capping and sealing under rainfall, but also primarily under the irrigations that are applied. So, you might have 14 or 15 irrigation events over the course of a crop, for example, in salad onions. So this sealing and then on dehydration capping of these soils results in significant reductions in emergence. So the examples here on the right-hand side are spinach seedlings trying to emerge through a crusted capped soil, poor establishment in onions, and again, poor establishment in field-grown herbs. And this poor establishment then gets translated into poor uniformity, an increased number or an increased percentage of the crop that is out of spec. It's too small or too large, and therefore a reduction in marketable yields. So if we just look at, this is an example here of the intensity of tillage operations. This was our parsley trial this year on what is considered to be a silty clay loam, but actually is 78% quartz and plagioclase feldspar, so it's a very, very fine sand. They'll have 2 passes of this power harrow, and then followed by a roller. So they've drilled after this power harrow, and then they'll go through and roll. And you can see here just how light this soil is, that it's blowing away. So there's quite a lot of challenges around managing these soils, which are really very prone to capping and sealing. So the way that polymers work, the polymers that we're using are used ubiquitously around the world for potable and wastewater treatment. So they're flocculants. They have a very high molecular weight. So you're looking at 10 to the 6 Daltons, whereas your typical polysaccharides are 100,000 Daltons. So they're very large molecular weight polymers that are anionic. So they have multiple negative exchange sites along that polymer chain. And they are absorbed to clay surfaces and other negative exchange sites in soils through primarily cation bridging, but also through non-specific van der Waals forces of attraction. And as I say, research has been undertaken on these polymers for the last 45 or 50 years. Polymers as flocculants are widely used in the US under best management practice under the US EPA. And there's something like a million hectares of furrow irrigated agricultural land in the US where they use flocculants to drop the sediment out of the runoff so that the water can leave the field clear. So we're just looking at using that technology, but specifically applying it to the soil surface. So the challenge has always been, how do we apply these polymers? Because the polymers themselves, in their concentrated form, typically the polymer is suspended. These myceli of polymer are suspended in a brine, in a saline solution. If you then mix them with water, the polymer starts to unfold and you get very high viscosity. So you can't then effectively spray them. But then if you dilute them enough, then you get the polymer chain separation, and then you move towards a low viscosity product, but a low concentration product. And what we've been looking at mostly over the last few years is this applying the product in a brine to the soil surface. So we had a PhD student, Silvia Rapano. She was undertaking this research for the last 3 years, completed in 2021. And the first solution we came up with, or SNF came up with, was a dual fluid nozzle. So having two separate systems on the sprayer, one for water, one for the polymer, and they would effectively be mixing outside so that we eliminated these problems of viscosity. And we got some quite positive results. And we're able to apply the product to the soil surface, applied it in spinach and coriander successfully, significant improvements in yield. But it was a very complicated system. So we had a bespoke sprayer built that had a separate water tank and a separate polymer tank. Both had separate pumping systems, and it was mounted. The intention was to have it mounted on the back of the seed drill so that you could drill and spray at the same time. So the challenges with this, again, are these issues of viscosity, but we've moved on from that now, from the dual fluid nozzles, because of a change in formulation of the product, which now allows us to use conventional flat fan nozzles on a conventional sprayer. So I'd like to give you the results now of the salad onion trials that we did last year. So we had 3 trials over the summer, looked at emergence at typically around 2 weeks, depending on the time of year and the conditions. Then we looked at it between 23 and 30 days, and then we looked at it post-emergence and at stand establishment. There were, as you can see here, there were multiple irrigation events throughout this crop. The intention was to harvest these products, these trials, but unfortunately, right at the end of the season, we had problems with mildew. So our most fantastic trial I think I've ever done didn't harvest because it had mildew. The second one was harvested early for continuity. They had to harvest the second one early, but we did manage to harvest the third one. So I'll give you those results. So the seeds were drilled with an agricola precision drill, 7 drill lines per bed on 2-meter centers at a target seeding rate of 63 plants per linear meter and a depth of 10 to 15 millimeters. The trials were then irrigated with a Briggs hose reel mounted, a Briggs 40-meter hose reel with Nelson nozzles. Target irrigations each time of between 6 and 8 millimeters, but that did on a couple of occasions go up to 12. All the agronomy was managed by John Maynard. So the product that we are looking at is new Flowbond CCMS 50. It's classified as an inorganic soil conditioner, and the treatments we looked at were control 40 and 80 kilograms per hectare. Using a conventional sprayer. The sprayer was applied using a Hardy sprayer with flat fan nozzles. The tractor itself, the sprayer itself, the diaphragm pump was a little bit damaged. We can only run it at 3 bars. And we changed the speed of the vehicle to allow us to achieve the concentrations that we needed. So the crop is drilled, and then we go in afterwards and apply the product. And again, just to go back to this issue with viscosity, this new product that we have, the CC AMS 50, in its concentrated form, has a viscosity not dissimilar to water. But as you start adding water to it, its viscosity increases as you get this interaction between the polymer chains, and then decreases again when you get to about 10% concentration, it can still be sprayed. And this is something we'll investigate this summer. So all the trials were set up in the same way. So it's the randomized block design. So we're looking at 3 treatments, 40, 80, and control in 5 blocks, and the treatments are randomized within the blocks. 20 meters long with 5-meter run-on, run-off areas and a guard row in between. And the same setup was used for all 3 trials. So trial 1, looking at emergence 2 weeks after drilling, we were seeing between a 70 and 95% increase in emergence with polymer application. And there was a significant increase in emergence between the 40 and the 80 kilograms per hectare. And at 14 days, we were at or above the target seeding rate, whereas the control was still 50% emergence. Again, at 22 days, so a week later, the control is starting to catch up, but is still not achieving its target emergence rate. And we have actually exceeded this with the use of the polymers, but there's no significant difference between what should be 40 and 80 here. And then again, at 30 days after drilling, we still have this 20% uplift in emergence, effectively stand establishment, and we've exceeded that target drilling rate. I also looked at variability within the crop. So looking at the crook stage. So as the onions emerge, they go through this crook stage where the onion is still bent over, looks like a shepherd's crook. And you can see here that the control, where we haven't had the product applied, has significantly higher number of seedlings that are still in this crook stage 30 days after drilling. So that has real issues around the uniformity of the product. So if we look at this visually, so this is 30 days after drilling. You can see our 80 kilograms per hectare treatment. You can see the drill lines very clearly. The image below here, you can see a uniform stand establishment, and that the soil aggregates are remaining stable. So this is after multiple irrigation events. And if you look at the control here, yes, you can see some emergence, but the crop isn't as well established. You've got a capped soil surface, and the aggregates are completely broken down. Went back to the same trial again. So this is 70 days after drilling. And again, visually, you can see a significant difference in uniformity, development of the crop. And again, 70 days after drilling, you can see that the surface, the aggregates remain stable as opposed to this capped surface, and really poor uniformity. And again, this is the eureka moment that actually we've got something that works here. And then you go back another 20 days and this crop is absolutely destroyed by mildew, so we weren't able to harvest it. Trial 2, again, this was on a field that had already been planted to salad onions. This was a second crop. 16 days after drilling, we have this increase in emergence between 36 and 41%. No significant difference between the polymer treatments. The control starts to catch up. It's quite a cloddy soil, quite a cloddy seedbed compared to the first trial. But 36 days after drilling, we still have this 20% increase in emergence as compared to the control. But in this case, didn't get near that target plants per linear meter, primarily, I think, due to the cloddiness of the soil itself. And again, we get a similar result in trial 3. But really, in this one, it's only the 80 kilograms per hectare that is really showing any uplift. until we get to 30 days after drilling. And then we've got this consistent, across all of the treatments, we get this consistent 20% increase in emergence with the polymer application. And then we looked at harvest. We harvested a 5-meter plot within the 20-meter, a subplot within the 20-meter plots, counted every single salad onion, weighed them separately, graded them according to the GSIS specifications, and then looked at the number of bunches per treatment. And we do get a significant difference in yield between the 80 kilograms per hectare and the control. So from the salad onion point of view, in conclusions, we do, across trial 1 and 2, we got between a 70 and 95 and a 36 and 41% increase in emergence, up to 16 days after drilling. And then in trial 3, across all 3 trials, 30 days after drilling, we have this consistent 20% increase in emergence as compared to the control, improved stand establishment, and actually the higher application rate resulted in a 20% uplift in yield. So I think the key points here is the fact that we've been able to stabilize the aggregates at the soil surface with what is actually a really low application rate of product, because generally there wasn't a significant difference between the 40 and 80 kilograms per hectare. And other incidental benefits were that because we have kept the soil surface open, uncapped, and unsealed, we get improvements in irrigation. In fact, John Maynard was looking at reducing the number of irrigations because he wasn't losing irrigation through runoff from this sealed surface. Other incidental benefits are application. They apply nitrogen fertilizer as a granule twice in the season. And on the sealed treatments in the past, I've seen that being blown off into the wheelings, where if we have a rougher surface here, I think we're much more likely to keep that fertilizer on the bed where it will be more effective. So then we also did some trials looking at baby leaf spinach and parsley. This was with our project partners, Watts Farms. So in contrast to salad onions, you're looking at between 9 and 14 or 10 and 14 days at that time of year for emergence, whereas spinach, we're looking at 5 days. So 5 days after drilling, the spinach is emerging. And again, with the application of the polymer, we get this really quite significant increase in emergence. 5 days after drilling, a 70% increase in emergence. 6 days after drilling, so going back the next day, obviously, we've still got this 50% increase in emergence, no significant difference between the 2 polymer treatments. And then again, 7 days after drilling, this is, you've basically, again, you've got this consistent 20% increase in emergence, and we've exceeded that target emergence per linear meter. I then went back again 15 days after drilling. So that was emergence, but I wanted to look at stand establishment because the spinach crop typically prior to 2 true leaves suffers from Pythium wilt. So you get a dieback of the crop. But again, we have this consistent 20% increase in yield, and we've exceeded this target emergence rate. So all really positive. You can potentially see some differences in stand establishment. The controls are a little bit gappy, potentially, as compared to the treatments. It was mechanically harvested. So these were 50-meter long plots, so that they could be commercially harvested. Collected that harvested product, weighed it, and then looked at the yield per plot. So I need to move this out of the way. It should have come through. there wasn't a significant difference. It was quite frustrating. There was no significant difference in yield between the treatments. But we think that this is largely due to the fact that in the controls, so the imagery here shows you that in the control, you've got a larger leaf, and this is a baby leaf salad, this baby leaf spinach, and a much denser crop in this 80 kilogram per hectare treatment. So this 20% uplift in emergence actually is resulting in a higher proportion of smaller leaves. This was supposed to go into the QC check within Watts Farms, but it's an incredibly busy time of year for them, so we didn't get that QC done. But visually, we can see that there's a difference in leaf size and plant density. And then we had the parsley trials. This was on this really very light, very cappy soil. And again, 16 days after emergence. So we were getting a significant difference in emergence between the treatments. And again, higher emergence with the higher application rate of polymer. Not actually getting anywhere near. So 36 days after emergence, really challenging field. Multiple irrigations applied. And although we got a significant increase in emergence as compared to the control, we didn't get anywhere near, or across the whole field, didn't get anywhere near the target emergence rate. But again, similar to the salad onions, we get a significant improvement in emergence. You can see the 4 drill lines for the treated plots as compared to the control without the polymer application. And again, here you can see that the surface has remained stable for the treated plots as compared to a very significantly capped surface here on the control, where you've got really quite poor emergence and establishment. At harvest, we harvested, well, they harvested in bunches. The pickers came, the most experienced pickers were harvesting these plots. And although we didn't get a significant difference in yield, I think there's a trend for an increase in yield. Just it's a very noisy control here in terms of yield. I think the parsley is largely compensating for space. So where there have been gaps in the emergence or reduced emergence, those parsley plants have adapted and put on additional biomass. So in terms of the conclusions from the spinach and the parsley trials, for spinach, we are getting 70, 50 and 20% increase in emergence 5, 6 and 7 days after drilling. You can see that there's a significantly more dense crop, which actually lends itself to baby leaf. Because the baby leaf specifications, it needs to be between 4 and 10 millimeter length of leaf. And for the parsley, again, we get this increase in emergence, which is what we're looking at. But unfortunately, this didn't translate into an increase in yield, but there was a trend for an increase in yield. And that's it. I may have gone a little bit too quick, but that gives us more time for any questions.
Okay, thanks for that, Rob. There is a couple of questions, and I was in the process of writing one.
Okay. Do I need to look in chat?
So, Tim Chayman, do you want to unmute yourself?
Yeah. Yes, thanks, Charlie. Hi, Rob. Long time
Hi, Tim.
no see. Hi there. Yeah, my first question was, what actually promotes the intensity of tillage? I know it wasn't part of your experiment, but it seems to me that's an underlying factor in you having to do this work. Is what drives that tillage, the intensity of it?
Primarily it's the small seed size. So to get a good soil seed contact,
Right.
and it's all about uniformity and stand establishment. So you think for spinach, which is actually quite a large seeded crop, you'd have thought that would have sufficient vigor to emerge through the crust. But these are soils that have been continually in horticultural baby leaf sort of production systems for many years. And you know, it might be used by one company for salad onions, and then the next year it's used for parsley for another, for example, or spinach. So these are intensively cropped, and that essentially has resulted in a structureless soil, which is why it's so prone to capping. Their solution, typically, to overcome these issues of capping are to apply repeated irrigations. So to avoid the cap forming, you have a seal, which can still limit emergence, but they're typically over applying irrigation, which also causes aggregate breakdown and further consolidation of that seal to keep the surface wet. But mainly it's just soil seed contact, and these are structureless soils that have been overworked, essentially.
Yeah, I guess, you know, where I'm coming from in terms of soil compaction and damage from vehicles, that's going to be a big factor in driving the amount of tillage. And the irrigation part of it, I recently read up on some work in California where they found that if you didn't apply traffic and you've got a reasonable tilth, then the irrigation event, okay, it was flood irrigation there, which obviously is different, but it didn't actually increase the capping on the soil. It was a Wasco sandy loam or something, but yeah, that was an interesting one. And I think part of the solution obviously is taking away the traffic that invites the extra tillage. The soil will naturally maintain its fine state if you don't run all over it. Okay, there's an irrigation factor involved, but it's only part of the story. Sorry, just follow the other question was just interesting. Was there any interaction between the amount of mildew in the crop and the application of the polymer?
No. It was the whole country.
Oh right, I know.
So the whole country. So I was talking. So presented to the R&D committee, the British Onion Producers Association, Processors Association, R&D committee meeting, and they were all saying that they had problems with mildew last year. It was just that warm, wet sort of end of July, early August. Yeah.
And I know it's an annual problem, isn't it? Ventilation of the crop is quite one factor to try and reduce that. But obviously, the more ventilation you got, the less crop you have.
Yeah.
Okay. Thanks, Rob.
Thank you.
Okay, Chris. Next question.
Hi, yeah, Rob, that was a great talk, nicely focused and to the point. But do these polymers, do they have a lot sort of long life in the soil? I mean, will they eventually build up, and would that be a good thing to improve soil structure? And the downside is if they don't, do they just sort of break down into smaller bits and you end up with lots of microplastics? I just see that Lancaster University have done a paper on microplastic levels in the Broadbelt long-term experiment, and I don't know if it wasn't very clear what the source of this microplastics is, whether it was from tractor tires or just generally blows in off of the surroundings. But so basically it's really the longevity and its longer term effect on soil structure.
Okay, no, that's very interesting actually, because this is something that I want to look at going forwards. So in terms of the aggregate stability and what's happening, because you've stabilized that aggregate, actually you're allowing that aggregation and the process of aggregation within that aggregate to continue potentially. So I'd like to look at that in more detail. And you're going through repeated wetting and drying cycles as well, which is quite interesting. So there's been quite a lot of research on this because these polymers are used in the wastewater treatment as flocculants. There's been research done across Europe looking at the potential long-term buildup of these polymers in the soil and there's no negative impact on soil biology, and there's no indication that they're accumulating in the soil. And you think about, you're only applying, so you're applying between 40 and 80 kilogram of product. Now, there's 50% of that is the solution we're using to prevent the viscosity issues.
Yep.
Then of that product, I think 30% of it is active ingredient. Okay, so you're actually applying a very, very small amount of polymer to the immediate soil surface. They're not classified as microplastics because they don't have cross-linking. They're linear products, so they're not, according to European legislation, classified as microplastics.
So they don't break down into microplastics?
No. So they're not themselves considered to be microplastics, and they won't break down into microplastics because they're not considered microplastics. If you were to look at some of the superabsorbents that you have, which are based on the same chemistry, actually, because they've got cross-linking, they're considered to be microplastics now, which challenges their application in an agricultural, horticultural context. So they do break down, but to be classified as biodegradable, they need to break down into lengths of 1,000 Daltons, I believe, and you're talking about 10 to the 6 Daltons. Okay, but I see your point about so you would have to have potentially repeated applications of this product, and I wonder what the long-term benefit is in terms of aggregate stability, so that over a period of time you might not need to. And then going back to Tim's point, if we can do anything to reduce trafficking and tillage, we would improve aggregate stability. So a lot of the growers that we're working with are looking at putting in a 2-year herb grass lay to improve aggregate stability in the longer term. And actually this year, when we're trialing in the trials, John has got a sprayer that's going to be mounted on the back of the seed drill made by Team Sprayers, and looking at band application over the drill lines. So again, minimizing the amount of product that's being used as well. So hopefully I answered your question.
Yeah, that's great. Thanks a lot.
Yeah, I think there's a number of questions sort of around that. So the next question from Jim, do you want to unmute? The question is, so again, he's talking about, does the product move downwards in the soil during heavy rain? And if the product remains on the surface, does it biodegrade in sunlight? And if so, how long does that process take?
I've not come across any evidence that it biodegrades. It is a stable polymer, and once it's bound, and this is why it's actually really effective in soils as a flocculant. Once it's bound to the soil surface, it won't break down and it won't move through the profile. Okay, so we are effectively its immediate contact on those exchange sites on the soil allows its very rapid absorption onto the soil, exchange site soil surface, and stabilization. And there's no evidence at all of its being able to move through the profile. It's bound. It's a flocculant.
I think so. Does that answer your question, David? And probably Declan as well. A similar sort of question around the product. Is it a synthetic or is it natural? Does it stay in the soil? Does it get taken
so that's a good question. So it's a synthetic polymer that's widely used in the water treatment industry as a flocculant. It's called Flowbond, is the group of polymers that they market. Other natural products have been obviously tested, and they've been tested against these synthetic products, and they are never as effective as the synthetic products. So the company itself is looking at seeing whether or not they can develop some biological or some organic, some natural polymers. So you can get starch-based products, you can get sodium alginate, it's a seaweed derivative. So there are alternatives, but none of them are as effective as these polymers.
Okay. Does that answer your questions, David and Declan?
I'm not quite sure. Very interesting talk, by the way, Rob. But if you apply this several years in running and then you stir the soil up, you're actually moving it through that soil profile. So what actually stops it then being taken up by the crop itself through the root structure?
Can't be.
It can't be.
It can't be. It is a stable molecule, and there's lots of research done on this. So during the synthesis of these polymers, because they're polyacrylamide based. I know the word acrylamide sends shockwaves across the food production sector, but there's a 0.01% residual acrylamide monomer as part of this synthesis of these polymers, and that is broken down in the soil naturally within 18 to 24 hours. Lots of research on this, and it's not taken up by the crop. And we've done research in Kenya where we applied this product to French beans, and then we analysed that crop to see whether or not there was either product that had been sprayed or product that had been taken up. And there's no detectable level of the acrylamide monomer is what we're concerned about. And I've actually just got a load of papers and reports on the biodegradation of these polymers in soils, which I only got it last week, so I need to read up on that in more detail. But there's quite a lot of research done in the US on this because it's accepted as a best management practice under the US EPA. So we use anionic polymers because they have no negative impact on the aquatic environment. If you use cationic polymers, they tend to cause flocculation and sedimentation around the gills of fish. I think that's the negative impact, or one of the negative impacts of the cationic polymers. And you think logically, cationic polymers would be much more effective because they can bond directly with the negative exchange sites on soil and don't require any cation bridging or anything like that. But just from an environmental impact point of view, they have a negative environmental impact, so we don't use them. And again, I hope I answered your question.
Sorry, yes, you did. Thank you very much.
The work you've done is very good and very well presented, a lovely piece of scientific work. You have a hypothesis, now you have you've drawn a conclusion that holding the structure together with polymers works. But I think what you're also doing is looking at other ways of holding the soil into clumps, if we call it that, which I think is a wise thing to do, because the word polymer may have customer resistance in the future. But the whole principle of what you're doing has been proven now. You've done a great job on it. But it's private industry will push the polymer, but whether the customers will stick with it, that's all I would say.
Yeah, no, it's interesting actually, because for years I called it polyacrylamide for what it was. And then talking to Bakkavor, they were the ones that we originally requested us to look at this. And it went all the way up to their sort of decision makers. And because it had the word acrylamide in it, they wouldn't fund it, even though this product is used globally in the water treatment industry, in cosmetics, in a food context as well. But I think it is a soil conditioner. It's classified as a soil conditioner. Some of you may have enough institutional sort of memory to, there was a product on the market in the 80s and 90s called Soiltex, which was used in the horticultural industry it was a granular product, and they used to apply it above the drill lines of brassicas and also for onions, and it would swell. So it's a bit like the super absorbents, and it would swell and crack the surface to allow the crop to emerge. And that was widely used, but the challenge was that you couldn't apply it to the soil surface, and it was messy. You know, it gets wet, it becomes very viscous, very slippery product to work with. So I think having it, maybe just calling it a soil conditioner, because essentially that's what it's doing, rather than a polymer, would be probably a better way going forwards. But there's a lot of industries. So far this year, we've got 3-4 different bulb onion growers that want us to run trials. There's more salad onion growers, and there's more baby leaf growers and herbs that want us to run trials as well.
Okay, a quick question from
the residual herbicides as well. I just saw that one. There is some wind erosion control, another one. Potentially that's what we're looking at with G's this year. And there is some evidence of its affinity to herbicides. So you might have less herbicide application because particularly the residual herbicide. Pre-emergence, is it pre-emergence? That was you were wanting to evidence of that as well.
Okay, I was just going to ask a question about the actual application. Is that twin nozzle or that twin fluid arrangement being used before? I've never seen it in agriculture, and I'm only aware of it in sort of more thick, gloopy, viscous liquids where they're mixed in the tube, like glues where they're mixed in the tube. I've never seen two materials blown together.
I have had conversations with Paul Miller about this in the past. I believe it has been used. There's a John Deere twin fluid nozzle, so it's a similar sort of concept. But you have to have a bespoke sprayer made with two separate systems to keep the products apart and the product and the water apart. But with the new formulation, we can use conventional spray equipment, but we still have the challenge of the wash down.
Yeah. Because
you've got to remove the product from the sprayer, and then actually you've got to have that wash down procedure. And the wash down procedure is basically a bleach solution. So a 5 or a 10% solution of bleach to wash the sprayer out. And that's what we need to, I think the final stumbling block.
Yeah, that's quite special.
In terms of the practicality of using these products, is to do that, and maybe replacing the filters on each of the nozzles. Yeah, making sure they're clean, making sure you're cleaning out the filter in the actual sprayer as well, to make sure it's thoroughly clean, because you've got any of this product left, it will still form a gel. So we really need to nail this down. So
yeah, some tricky mechanical things to get.
Yeah, and also we were talking to G's for the trials this year, and they wanted to use their 6,000 litre 48-metre boom sprayer for a product that's applied at 40 kilograms per hectare. It's not the right way to go. So having something mounting on the back of the seed drill so you can drill and spray simultaneously as a single pass would seem the most logical way to go.
Yeah. Okay. There's a question from Juan. Do you want to unmute yourself?
If there's a question from Jane Ritson, can you deny it, please? Because she's only sitting next to me.
Making notes.
Yeah.
The question is that if this product stays in the soil for years or decades, there's not any potential long-term impacts. There's no potential that these polymers will react with other substances or create cross-links with other chemicals in the soil or with the biology that is in the soil.
There's no. So this, I can try and send you the paper there was a cost action looking at the long-term application of basically sewage sludge, and sewage sludge is flocculated using these same products. And they were looking at the long-term application of sewage sludge to see whether or not there was any evidence that there was a buildup of these particular chemicals or products, and there isn't. And there shouldn't really be any interaction, because the synthesis of these products means that you create essentially a very stable chain, and that chain, once bound to the soil surface, is bound to the soil surface. So it can break down, but I've got the evidence somewhere, the information on the half-life as well, which I can potentially share at the next presentation. I'm happy to do another presentation at the end of this season, if that's okay.
That will be great. Thank you.
Okay, I think you answered Jim's question, didn't you?
I've got a question from my neighbour.
Read the chat. I'm not.
Who's just punched?
Read the chat.
Oh, she punches me. Did you see that? No. So the economics. That's a very interesting question, Jane.
That's why I asked it, Rob.
Very good. So the presentation I made to BOPA a couple of weeks ago, the presentation before me was looking at nitrogen fertilizers, and the cost of those products range from 480 to 630 pounds per hectare, with no significant impact on yield at all. Okay, we are looking at costs of 360 pounds per hectare, and we've got evidence of a 20% increase in yield. And if we go to band applications, then we're using less product. And if we can apply it at 10% dilution, or diluted 90%, so a 10% concentration of product, we'd be using less product, but the polymer would be open, fully open. So much more opportunity for it to act like almost like a spider web sitting on the soil surface and having multiple points of contact for stabilization. Could it be used as a binder for organomineral fertilizers? Funnily enough, we're having conversations around that as well. Yeah.
Okay. Oh, one more question.
So does the yield increase and erosion control justify its costs? What do you think, Jane? Sorry. So yeah, one of the things we haven't looked at is the erosion control side of things, because the focus has all been on the emergence and stand establishment and benefits on yield. So I have some ongoing conversations with Southern Water in the Western Rother, where they have major problems with sediment. And actually their AMP8 is all about sediment and sediment control. So the evidence from what we've seen in the field is that you've stabilized the aggregates, and if you've stabilized them, you don't get the supply of material that can be then transported off site. So I think from an erosion control point of view, I think they also have benefit, have merit as well.
Okay, cool. One more question.
Not
Jim?
from Jane, I hope.
No.
Okay.
I don't think Jim
Crops
can
that you would not want grown in a soil that has so. There's no, I don't think there's any evidence of that. Well, it's a good point though. Typically, I have to say, if we spill the product when we're pouring it into the sprayer, or we spill it anywhere, the most effective way of cleaning the product off is with a handful of soil, because it flocculates so well. You can wash it off because it just becomes viscous. So it is bound immediately to the soil. It's something that it's something worth looking at, I think. So if for example you've got fields where you've got issues of Pythium, or you've got issues of PCN or other Fusarium, for example, and you don't want to transfer to a sterile, clean site, then yeah, that's something that could be considered. Might have a wash down procedure for the implements. Yeah.
Okay, fascinating stuff.
Thank you, Jim, for giving me more work to do.
Yeah, some really good questions there. Brilliant. Okay, well, I think that's about it. Questions, and we're not far off the hour. So if there are no more questions, then I'll I'll draw things to a close and say thank you to Rob for giving us a really interesting presentation. Fascinating stuff. Thanks for taking your time out to do so.
That's right.
Much appreciated. I think, judging by the questions, everybody found it really interesting. So I'd like to thank everybody for joining us today, and I hope you'll join us for our next lecture on the 12th of March, where we'll be joined by Nick McCarthy from Cenex, who will be talking about net zero and the farm of the future. So all that's left to say is thanks again, and we'll see you next time. Bye-bye.
Okay, thank you very much.